Hi everyone. So in the last video we have shown that the OLS estimator in the multivariate case can be written as x prime x inverse x prime y. And that is the matrix form expression that describes the OLS estimator for a set of beta parameters that are all included in this vector, okay, for k independent variables, including a constant term. Right. So in this video, I'm going to show you briefly how to program this in R. And as you will see, this will require even less code than the bivariate specification that I showed you in the previous videos. Okay. We're going to call this function OLS. And this function will have two separate inputs. One is y, the vector of the dependent variable, and one is x. Note now that this is a capital X, which is a matrix, okay, a matrix of independent variables, including a row of ones for the constant term. Actually, no, the row of ones for the constant term, we will, this is what the second line of code does here. We have the matrix of independent variables, x, and what we're doing here is we're adding a row of, a column of ones to that x matrix in order to estimate the constant term beta 1. And then all we have to do is we have to translate this expression into R, which is fairly straightforward. The matrix multiplication, or the operation, or the sign for matrix operation is not just a star; it's percent star percent. So this is the notation for matrix multiplication. T is the notation for the transpose. So this is tx is transpose of x, so x prime, matrix multiplied by x, and then solve is takes the inverse of a matrix, so this is x prime x inverse, and then this is matrix multiplied by the transpose of x, so x prime, times our y vector, right? And then we can directly return this beta, and that's already it. That's all we need to run OLS in R by hand. So again, to kind of show you that this actually works, we can go back to our social pressure experiment that we loaded previously, and again we're looking at the subset of data, or the subsetted data. We're only looking at observations in either the control condition or the social pressure treatment condition. And now one of the things that we looked at in the past was this interaction effect between voting in the previous primary in 2004 and this messaging, the social pressure message treatment on on expected turnout in the 2008 primary, right? And so if we run this regression, I just did a little trick of taking the transpose of this vector of coefficients twice to have it in a nice format that fits in my presentation right away. Other than that, you can just ignore this part. The point is, we have 4 coefficients. We have an intercept, again, that's 23% expected turnout in the control condition. And since we have this interaction and we control for a primary 2004 turnout, this is the expected turnout rate among people, among observations that did not vote in the 2004 primary and that were in the control condition in the specific field experiment, right? So 23% in expectation, or 24% participated in the 2008 primary, okay? Turnout was in expectation, turnout was about 15 percentage points higher in the control group among people who actually also participated in the 2004 election. So people who participated in 2004 in the primary were more likely to participate in 2008. And the effect of the neighbor's treatment of the social pressure treatment was that it increased, in expectation, it increased the turnout rate on average by 6.9 percentage points among voters, among people who did not vote in the 2004 election. And this effect was even larger, and this is now the interpretation of this interaction effect. The effect of this treatment was even larger among people who participated in the 2004 election. So for those who participated in the 2004 primary, the effect of the social pressure treatment as compared to the control was basically 6.9 percentage points plus 2.7 percentage points. So almost 10 percentage points increase in the expected turnout rate among 2004 voters or people who participated in the 2004 primary who received that social pressure message. All right, so much for a recap of interpreting these interaction terms. And now we can get exactly the same result using our new OLS function. Our y vector is again just the primary 2008 indicator, so that's our dichotomous outcome variable. And our x matrix now contains 3 separate variables. And here, while we could here rely on LM and this formula specification to automatically generate this interaction term, here we have to do this kind of manually, right? We have our first variable, which is just the indicator variable, whether people participated in the 2004 primary. We have our second variable that is the treatment indicator. And then our third variable here, or third column in our X matrix, is the multiplication of the treatment indicator and the participation in the previous election. And so that's just primary 2004 times this treatment indicator. And if we run this with OLS, Y, and X, we see that we get exactly the same coefficients for the intercept, for the effect of the primary election, or sorry, I should say the expected difference for people who participated in the previous election versus not, as well as the expected difference in the treatment condition as compared to the control condition for those who didn't participate in the 2004 primary, as well as the interaction effect, right? So all these are equivalent, okay? So that kind of confirms that the formula that we derived step by step, starting again from the sum of squared residuals, now in vector and matrix form, results in a specification of the OLS estimator that is consistent with what the LM function in R is doing basically out of the box. So if you have been suspicious about the LM function before, I hope now I finally convince you that you can safely use it, because it indeed gives you the OLS estimates in the bivariate as well as the multivariate case. In the next video, I'm going to proceed to show that OLS in the multivariate case is also unbiased.